Hi everyone. So today we are going to discuss about the basic concepts of open sets, closed sets, and we will solve some kind of problems there. Okay. So first we will start from some basic problem. Then gradually we will go to harder problem. So let's start with the definition. Before starting, let me present the screen once again. Uh, can you hear me? Can you hear me? Is the screen visible to you? So, um, so first let's start with the concept of the definition of open set. So, let open set. Consider the open interval AB. First of all, this is an open interval. So, I mean, by name it is open interval, but this is an open. One second, sorry, there is an issue in the with the one node. Just hold a second. So, this is an open interval AB. We will show that this is an actually open set. So, for open set, what we need to choose? What we need to do? We will choose a point x from the open interval AB and we'll see that can we find some kind of open ball that is inside the open interval AB. So this is x, okay. So choose epsilon to be distance between mod x minus a and mod x minus b by 2, the minimum of these two epsilon. Then observe that bx epsilon subset of open AB. How? Because look what is epsilon. Epsilon is the distance between x minus a, half of the distance between x minus a, and half of the distance between x minus b. Its minimum is the epsilon. So let's is the minimum. So this is the half. So bx minus epsilon, bx plus epsilon subset of open AB. That's how it is true. So open interval is an open set. So open interval of R is open set in R. Okay. Then, mm, then the next. So consider the following example that take S to be 1 half 1 third 0 dot dot dot. So we need to check the int S. Int S is what? By the way, int S is the collection of all interior points. So what is the interior of S? Observe one thing. This set is like this is the 1, this is half, this is 1 third, this is 1 for dot dot dot. Suppose x belongs to int S. Suppose x is the interior point. This means what? This means for epsilon, for there exists epsilon greater than 0 such that x minus epsilon, x plus epsilon subset of S. But this is not possible because x minus epsilon contains a point of a constant infinite number of points, but actually this set S is some kind of discrete set. So this whole interval can't be inside S. That's why int S for this case, for this subset S, interior is empty. Okay. So now consider S to be n. For the case of natural numbers, what is the interior of S? So here the same argument. So this is 1, 2, 3, 4 dot dot dot. Okay. Now we take its interior. So what we will do? If suppose x belongs to int s, this means what? X minus epsilon, x plus epsilon, it is a subset of S for some epsilon greater than 0. But this is not possible because the set 1, 2, 3, 4, it's kind of a discrete set. So it can't contain any type of open interval. That's why interior of natural set of collection natural numbers is empty. So yeah, that's it. So now so again consider our example, that is consider the previous one, s equal to 1 half 1 third 1 4 dot dot dot. The question is s open? The answer is not, because we've already seen that interior s is empty set. So if s is open, so interior s can't be empty, interior s must be s. S should be equal to interior s if s is open. So s not open. By the way, one thing to note that S is not open set, well, but it does not mean that S is a closed set. Okay, so open, not open does not imply it is closed. Okay, there are sets which are not open and not closed. So come to the next example. Mm, one second. For any subset of R, interior S is open in R. How to do that? For any set S, its interior is a collection of open sets. Okay, so it's just a matter of definition. So suppose it is our S, and suppose x belongs to interior S. So what do we need to do? We need to find a epsilon greater than 0 such that bx comma epsilon subset of interior S. Now since x belongs to interior S, so this implies what? Bx comma epsilon subset of S. So suppose this whole thing is bx comma epsilon. Now obviously this whole bx comma epsilon subset of interior S, because this bx comma epsilon is actually open. So obviously this lies inside the interior. So that's why interior of any set is an open set. So now there is another question. Show that interior of S is largest open set contained inside S. So this means what? Interior is the largest open set contained inside S. Sorry. First of all, interior S is an open set. So first observe the interior S is open set. Now in addition to the largest open set. So how to do that? so that it is largest. Containers, obviously interior of S, a subset of S. Now we need to check that uh, it is contained inside. Now we need to check that it's the largest. So suppose U be an open set inside S, that is U subset of S. We need to show U subset of interior S. Now that's obvious. Why? Because we already know that U is open, so if we take any x belongs to U, so we will find some epsilon greater than 0, so the b x epsilon subset of U subset of S. So for the epsilon b x epsilon subset of S, this implies what? This implies x belongs to interior of S. So U subset of interior of S. So interior of X is the largest open set contained inside S. So this is the one thing, and mm, so it's a theorem. It's a well-known theorem. You can find it in any standard book, but just for the remembering purpose, let's recall this theorem. Any non-empty open seat in R is the union of countable collection of disjoint open interval. So this tells that any open set is in R is the union of countable collection of disjoint open intervals. So actually, it's a very well-known theory. We can find it in any book. So just let me introduce a notion, some called a basis. This property, which is being satisfied, is known as a basis, and this is usually started in a point set topology. So there's one thing I thought I should mention. Yeah, there is something called the limit square. So first the consider the again set same set one half one third one fourth order. Then show that every point of S is isolated point. So but by what by isolated point we mean what? Just for recall, isolated point means, so let S point belongs to A said to be an isolated point if there is epsilon greater than 0 such that n s comma epsilon intersection S is equal to only singleton x. Sorry, S, yes. So this situation is on the isolated point. So consider this set. This is one, this is half, this is one third, this is one fourth dot dot dot. Now, so first consider the point half. If we choose a very small level around half, This and intersection of S is only half. Similarly, in case of point one third or similar case situation in the point one fourth. So every point here is an isolated point. So every point is an isolated point. So the next thing is that consider S to be equal to Z. Now question is the find the isolated points of S. How to do that? So observe one thing that this is Z 0, 1, 2 dot dot minus 1 minus 2 dot dot dot. So if we choose any point 1 and choose a very small neighborhood, small epsilon neighborhood around 1, then this neighborhood intersects Z only contain the singleton point. So this neighborhood intersects S singleton point. So all points of Z are isolated. So all points of Z are isolated. Now, one thing, another, for example, now consider sorry, S to be Q. Now, question is find all isolated points. How to do that? So, I mean, consider any rational number and consider very small epsilon neighborhood around Q. But the point is that since Q is dense in R, so any small enough neighborhood will contain infinite number of rational numbers. So this intersection, this open neighborhood intersection S is not the singleton Q, it's more than that. So, no point of Q are isolated. So no point of Q are isolated. Oh, one second. Yeah. There is another thing which is known as, so this is like we need to show that finite set has no limit. Finite set has no limit point. How do this? Suppose S is a finite set x1, x2, etc. Limit point means what? For any epsilon greater than 0, in prime x comma epsilon intersection A should be non-empty. That's the limit point. So if we consider the point x1, suppose this is x1, this is x2, this is x3, dot dot dot. And if we choose a small, very small neighborhood x1, then this neighborhood intersect S, it contains only single response. So no points are limit points. So no points of S are limit point. That is zero limit points is everything. There is another thing that we need to check is that, well, probably I'm going to turning off my camera because there is some internet issue I realized once. So you need to check that the show that n has no limit points. So how to do that? So probably there is one logoshrem. So can you just tell me how to show that n has no limit point? Just think about it for 1 minute. Sorry. Okay, so how to show that this n has no limit point? So we can do it as follows. So consider the next set of natural numbers 1, 2, 3, 4 dot dot dot. Now consider the open intervals around any point. Very small neighborhood. So consider the point 2 and the small neighborhood around 2. Now this neighborhood contains only point, this neighborhood contains no point other than 2. So this 2 is not, so 2 is not a limit point. Hence n has no limit point. In other words we can say that n, sorry, limit point, so n dash is equal to 5. This is one thing. So there is a very well known theorem, just for recalling purpose, let me write it down. This theorem tells that every bounded infinite subset of R has at least one. So it's a known as Bolzano. So now there is one some. Can you prove that following? Suppose A and B subset of R and assume A subset of B. Prove that interior of A subset of interior of A. Logically, can you think about it? How to solve this problem? Okay, then think for a couple of minutes. So we can do it as follows. A subset of B, we need to check the interior subset of interior B. So take X from interior of A. This means was there epsilon greater than 0 such that this open ball B epsilon subset of A. And it is obvious subset of B. So Bx epsilon subset of B. This implies what? X belongs to interior B. So that's how interior subset of interior. And one another thing is that show that interior of interior A is equal to interior A. Or A is subset of R. Prove it. Anybody can prove that interior of interior A is equal to interior of A for any A subset of R? Anybody just think about it? Well, no issue. We have already seen that interior of A is open. Now the interior is open, so obviously its interior will be same thing. That's how we can say the interior interface is equal to interior of A. Then, yeah, there is something, some notion known as the closure of a set. What is saying? Suppose A is a subset of R. Yeah, suppose A is a subset of R. By closure, we mean the A union the set of all limit points. And by closed set, the set A subset of R is said to be closed if A subset of R is said to be closed if A contains all its limit points. This is known as the closed set. So, for example, so if A collection of unit points A dash is empty set, then obviously A must be closed. So, set of integers, set of natural numbers are closed in R. So now let's calculate some closures. So how to calculate the closures? So suppose A is equal to open AB. Prove that its closure equal to closed A comma B. Well, so how to prove it? So you can just think about it, or else I will explain. Well, so take S to be AB. We need to show the S closure equal to closed interval AB. So what is this? By definition, S closure equal to what? S closure equal to S union the set of limit points. So enough to show that point A and B are only limit points of S. Okay. So observe that. Now consider the number line. A. This is B. So A is the limit point. How? If we consider any open neighborhood around A, it will be like this. So obviously this open neighborhood minus A intersection open interval AB is non-empty. That's how A is a limit point. And similar reason, B is a limit point. Now we need to show that no other point except 1 and B can be limit point. So consider the point outside the set capital S and assume that this is lying left of capital small a. So if we take any small neighborhood, then it is not intersecting even the open interval AB. So any point, so this point is not a limit point. So due to this argument, any point will be a limit point. Sorry, no, M. So due to this argument, any point x which is not equal to a and b a limit. Sorry, are not limit point. So that's how S closure equal to open interval B. So one second. So the another question is that take S to be 1 half 1 third 0. Then find the set of all limit points of S. So the set S is one half 1 minus order. We need to check its limit. So can you think just think about for 1 minute? Else I will tell you. Yeah. So S is one half 1 third dot dot dot. So first observe that 0 will be a limit point. Okay. Why? Because if we take any small neighborhood of 0, but Archimedes property 1 by n is less than epsilon, but 1 by n is a say point in it. So 0 is a limit point of S. There is one limit point of S. So 0 is one limit point of S. So what about the other limit points? Think about it. So just think about it. Oh no. So any point which is not 0, 1, sorry, 1 half 1 third. So if you choose any point like this, so you can consider small neighbor 1/4 which does not contain the successive two terms. So 0 is only one limit point of S. That's why S closure equal to S union 0. Okay. Yeah. So so once again let me think which question I can solve actually. So question is important to solve. Yeah. So consider the following question. Took S to be 1 by n, 1 by m, n belongs to n. First question is show that 0 is a limit point of S. And second question is find S dash. Third is, yeah, find S is the second question. So we are giving the set S equal 1 by 1 by m. We need to check 0 is the limit point and we need to check that we need to check the find S dash is our limit point. So just think about it. I will be back within 2 minutes. So, anybody has done? Well, no issue. So, one second. So, how to find the ace dash? So, first of all, what is, I mean, this set contains this set like this 2 by small n belongs to n. Now, observe since 2 by small n, this sequence converges to 0, hence 0 is the limit point of S, right? Yeah. So, 0 belongs to S dash. Now, what are the other points in S dash? So, fix a m belongs to n. Now observe that this sequence 1 by n plus 1 goes to 1 by m naught. So 1 by m naught is the limit point of S dash. So S dash equal to S union 0 union the set 1 by k belongs to natural is the, this is the S closure actually. So yeah, that's the S closure. So in this solution, does anyone have a problem? Let me know. I am waiting. Or else we'll go to the next problem. Okay. Just let me know, does anybody got Sorry, I mistakenly muted my mic. So just let me write describe it once again. So here we need to check that is Q closed in R. Thing is Q closed, you need to check. So if Q is closed in R, then Q closure equal to Q. It has to be. But you see, since Q is dense in R, so Q closure equal to R. So this together gives R equal to Q, which is a contradiction. So Q is not dense in R. Yeah, that's why we can say this. That Q is not closed in R. So finite subset of R is closed. How to prove it? It is a finite subset. And in order to close it, we need to check that all of its unit point lie inside of the set. So just think about it. Okay. So suppose this is x1, this is x2, this is x3, x4 dot. So a finite subset. So you need to take its limit point in order to show it's closed or not. So consider this point x2. Now if you choose a very small neighborhood around x2, this will contain only x2 of the set capital S, where S is the finite subset. So the only limit point of this set is the empty set. So with the obvious subset of R, that the finite subset is always closed. And the next thing comes that once. Yeah. The another thing which we need to prove is that prove that closure is the smallest closed set containing A. Let's say the closure of a set is the smallest closed set containing A. First of all, closure is a closed set. Because A closure equal A closure. So it is a closed set. And obviously A closure contains A by definition of this closure. Now we need to check that what is the smallest closed set. Suppose let F be a closed set containing A. So we can put F closures after A closure. So now if it's a closure, F closure equal F. So basically F contains A closure contains A. So this means what? F is the small, so is close. I mean A closure is the smallest closed set containing capital A. So due to this reason, A closure is the intersection of all closed sets F containing capital A. So that's how we can prove that closure is the smallest closed set containing that set. Okay. So Well, so till now, many things has been done. So I'm waiting for 2 minutes, and just let me know. Do you have any problem or any confusion or doubt? Then we will solve some another problems. Okay. So does anyone have any doubt? Okay, so it seems no. So well, so there's another question. Yeah. So prove that A subset of B implies A closure subset of B closure. Just think about it and observe on the following that closure is the smallest closed set containing that set. So just try to think about it, or else I'll write down the proof. Okay, so how to prove it? So what's the A closure? I mean, look. A closure means what? For any epsilon greater than 0, B prime x epsilon intersection and non-empty. So obviously now A subset of B, so B prime x epsilon intersection B. Now this implies what? This implies X belongs to B closure. So that's how A closure subset of B closure. And uh, also this one thing, and the other thing is that A union B whole closure equal to A closure union B closure. How to prove it? So how to prove it? Observe that A subset of A union B. So obviously A closure subset of A union B whole closure. Okay. So A closure union B closure subset of A union B whole closure. Now we need to check that A union B whole closure subset of A closure union B closure. Now observe that A closure union B closure is a closed set. Why closed set? Because the union finite union closed set containing A union B. So this A closure union B closure is a closed set containing A union B. And so by the smallest property A closure union B closure subset of A union B whole closure. So this relation holds. Yeah, in this way you can show that A union whole closure subset of A closure union B. So this directly tells us that So there is one other problem, is just that closed and closed amount interval is a closed set. So how to check that the closed bound interval is a closed set? So anyway, the closed bound interval is the form closed AB. And what is the closure? It's closure, it's closed AB itself. So it is a closed set. So well, till now, what has been done? I think we should give a small revision. Then we should continue. Okay. So just think about it for 2 minutes. Tell me if there is any issue or confusion. Else, I will start revising the whole thing. Okay. So I will be back after 2 minutes. Yeah. So does anybody have a confusion or any question? Let me know. So it seems that there is no, just one second. But it seems that there is no, okay, so let's just revise the whole thing. Okay. Well, probably there is some internet issue. I think there is. So I am gathered actually. So so let's start from the basic open set. Just a second. So open interval AB is an open set. It's a given thing. Okay. So no no. So here what we are trying to show. We are trying to show that open interval AB is an open set. So here what we have done. We have done that. So we have chosen a small x from the open interval AB. Okay. And we have chosen a very small epsilon around the small x. How the epsilon has been chosen? So how the epsilon has been chosen? Epsilon is the minimum of mod x minus a by 2 and mod x minus b by 2. Okay. So d with epsilon, you can check that dx epsilon subs to open interval AB, and in this way, open interval AB is an open set containing bx epsilon. So this argument tells that any open interval in R is an open set. Okay. Now choose S, the consequent set S equal to 1 half 1 third dot dot dot. So we need to check what is the interior of S. So by interior, what we mean? By interior, we need to check that if we choose any point from interior X, is it possible to find a small epsilon such that the epsilon neighborhood around X is lies inside the capital S. But it is not possible because if any open interval x minus epsilon and x plus epsilon lies inside the capital S, then since S is discrete sets, since all there is a distance between the all points of S, so an open interval can't fully lie inside S. So that's how interior of S is an empty set. So there is another question which tells that how we need to find the interior of the set of natural numbers. So here the argument is same. So if we choose any x and choose any epsilon neighborhood, we can choose epsilon very small such that this neighborhood does not contain any other natural number except the smallest. So the interior is empty. That's why interior of natural numbers is empty. So till now, does anybody have any problem or any confusion or doubt? Please let me know. So right now I am waiting for 2 minutes for your response, else I'll continue. So the next set is that S equal to 1 half, sorry, one second. S equal to 1 half, 1/3, 1/4, dot dot dot. We need to check that whether S is open or not. So, so first consider that we need to check what are the interior of it. Because S is open if and only if S equal to interior of S, right? So, I mean, since the set is a discrete set, if we choose any point x, then it will be what? It will be that x minus epsilon, x plus epsilon. This will be. I mean, this neighborhood can't contain. This neighborhood can't contain. Can't be inside the whole capital S. That's why interior S is empty set. So S is not open. Now, for any subset of S, subset of R, interior of S is an open set. Why? Because if interior of X, if X is inside the interior of X, this implies what? This implies we can get epsilon greater than 0 such that x comma bx comma epsilon is subset of interior of S. But obviously bx comma epsilon is subset of S, so bx epsilon is subset of interior of F because bx epsilon is itself open. Okay, so that's why interior S is open in S. Now here what we have done, here we have shown that interior of S is the largest open set contained inside S. That is, we need to check three things. One, need to check interior of S is the open set. Another thing is we need to check interior of S is contained in S, and last thing is that it is the largest open set contained in S. So first we need to observe interior as open set that we have just proved in the previous problem. And by definition of interior of S is subset of S. So we need to check that it's the largest open set contained inside S. So what we have done, we have taken even open subset inside S. And now we need to check use of the interior of S. One second, sorry. Now since x is in U, so since U is open, so Bx epsilon is also U subset of AS. So any non-empty open set, so I mean sorry. So x belongs to interior of S. That's how x U subset of interior of S. That's so interior of S is the largest open set contained inside of S. And there is one theorem is that any non-empty open set in R is the union of countable collection of disjoint open intervals. It's a theorem. And from here we can get a concept of basic, but right now it comes into points to model. Right now we are not going to get into the discussion. Okay. So just till now, let me know does anybody have any problem. So I will wait for 2-3 minutes. Then we'll go to the next portion. Okay. So I am waiting for 2-3 minutes. Just let me know if you have any question or doubt. If anybody have any problem, please let me know. I'm waiting. Okay, so it seems that okay, so nobody is there. No issue. So yeah, yeah. So consider the set A is equal to 1 half 1 third 1 4. We need to check that every point of S is an isolated point. So what is the isolated point means what? Means a point is an isolated point if there is epsilon greater than 0, so the deleted epsilon neighborhood of the point contains a deleted epsilon neighborhood of the point intersection S contains only sigma S. So consider the number line and consider all these points. So suppose choose the point 1 by 3 here. Then obviously consider the very small epsilon neighborhood 1 by 3. It contains only the point 1 by 3 and no other point it has. So the S is what? So S is us. So I mean every point of S is an isolated point. Yeah. So that's why every point of S is an isolated point. Once again. Yeah. So we now consider the S to be Z. So here we also need to check that also need to find the isolated point of S. So how to do that? So if we choose any random point, call it 1 in the sake of simplicity and consider epsilon neighborhood around 1. So this neighborhood contains only the point of 1 of S. So all points of Z are isolated point. So basically what does it mean isolated? Isolated means what? Means the points are there is a distance between the points. Some of the points there is distance. So there is no isolated points. Okay. For example, this is the open interval union some points. These 3 points are isolated points. So now consider now consider S equal to Q. So here we need to find the all isolated points. So how to do that? So I mean, if at some point isolated points is what we can choose epsilon neighborhood if small epsilon neighborhood this I mean such that Q minus epsilon Q plus epsilon minus Q intersection Q it has sorry hello any question or confusion? Okay. So yeah. So to consider the epsilon neighborhood around Q, so which is Q minus epsilon Q plus epsilon minus Q intersection Q, it is empty. So I mean it can't be non-empty because Q is dense. So very small open neighborhood even contain the rational number. So that's why all points are isolated. So that's why the Q has no isolated points. So, well, so till now, if you have any issue, just let me know. I'm waiting for 2 minutes. Let me know if you have any issue. Okay, so going to the next problem. So that here we have proved that finite set has no limit point. So one second. So how to do that? Suppose AC is point x1 or xn is a finite set. So in order to show that it has no limit point, what we have to check? We have to check any arbitrary point, and we need to consider any epsilon neighborhood around that point. We will show no, sorry. We will take any arbitrary point and we will take a particular epsilon neighborhood around that point so the intersection is empty. So suppose since x1 is to x2 is finite set, so obviously some discrete here. Obviously all are discrete. So if we consider a small enough neighborhood x2, obviously we observe that this small enough neighborhood does not intersect the other, does not find the other point. So n prime x epsilon intersection is not empty. Yeah. So due to this reason, S has no limit point. So now we need to similarly check that S n that the set of natural numbers has no limit point. So how to do that? So for example, consider 2 and consider epsilon neighborhood around 2. So this neighborhood does not contain any other point except 2, so n has no limit point. So that's why n dash is equal to empty. N dash means a collection of all limit points. Yeah, there is something known as the Wilder-Buster's theorem. Well, up to these, does you have any confusion? Please let me know. Else, after 2 minutes, we'll start. So just let me know any confusion. Well, so no confusion, I guess. So now let's come with the Bollinger versus theorem, which tells that every bounded infinite sequence of R has at least one limit point. So we are not going to prove this. Probably we can see the proof in the lecture. So here just we are recalling this uh, theorem. So come to the next problem. So suppose A and B subset of R. We need to prove and assume that A is subset of B. We need to prove interior A subset of interior B. So Logashri, can you tell me how to show interior A subset of interior B? Can you give me some idea? Okay, sure. So observe that if x plus interior is, we can find epsilon greater than 0, so bx epsilon subset of A subset of B. So now since A subset of B, so that's why bx epsilon subset of B. This implies what? X plus interior B. That's why interior of A subset of interior of B. This circle denotes the interiors. Okay. And the next, usually let me know, do you have any confusion in this proof or previous portion? Do you have any confusion? Okay, no issue. So just so I hope you are fine with all the groups and the statements, the previous portions. So here, to check the int of interior A subset of R. How to prove it? So proving this is similar same as saying that interior of A is an open set for any A, right? We've already proved the interior is open set. That's interior of interior is the interior. Okay. So till now, do you have any confusion? Please let me know. The reminder is back, so I'm turning my camera off. Sorry, once again. So so now we have introduced the notion of closure of the set. So intuitively, the closure means collect the set and together with the all limit points. This is known as the closure. That's why the definition is like that. That a closure equal to a union set of all limit points. Okay. Now what is a closed set? A set is observed set be closed if the set contains all of its limit points. Okay. So hence obviously if set of limit points a dash is empty set, so then A must be closed. So due to this argument, J are closed because Z and for Z and N, all points are isolated points. Hence, they can't be limit point. Okay. So till now things are okay or not? Please let me know, Lageshwari. Okay, so now we have here proved that if S is equal to open interval AB, then it proved that S closure is equal to closed interval AB. So in order to prove this, we need to show that A and B are the only limit points of capital S, right? I mean, if we can show this, then we are done. So, sorry. So enough to prove that A and B are the only limit points of capital S. So, first we have proved that A and B are the limit points. So here is A. So consider very small epsilon neighborhood remains with epsilon, and over this neighborhood contains points of S other than small a. Similarly, so A and B are the limit points of S. And if you took any point outside that set S, this implies, so then it will be what? So choose a point outside this AB. So consider the small enough neighborhood. And this neighborhood does not even intersect S. So the any points outside the closed interval AB will be not limit point. So S closure equal to S union set of all limit point, which is nothing but the closed interval AB. Let me know in this problem, does you have any confusion and doubt? Okay, so go to the next problem. Consider S to be 1 half 1/3 dot dot dot. So we need to find the set of all limit points of S. So here first you observe that 0 will be a limit point of S. Because if we consider 0, I consider a small neighbor around 0, that is if you consider this closed interval 0 epsilon, then we can find that the 1 by n will less than epsilon, that is this 1 n belongs to this set and this 1 by n belongs to S also. So 0 is a limit point. And what is the other point? If you take any point other than 0, then we can find a small neighborhood which does not even intersect capital S. So, so the 0 is the only neighbor on this set and that's a S closure equal to this. Now, sorry. Yeah. Yeah. Now consider the set S to be 1 by n plus 1 by n. We need to check the 0 is a limit point of this set. So how to do that? Here observe one thing that this set S contains 2 by the sequence 2 by n belongs to it. Now since observe the sequence 2 by n goes to 0, so 0 is the limit point. Why? Because any epsilon neighborhood, I mean, so because what? So 2 by n is less than epsilon for all n greater than or equal to k for some k. Because 2 by n goes to 0 and this is nothing but what? 1 by n plus 1 by k, and this holds for all n greater than k. So we can tell that 1 by k plus 1 by k, sorry, 1 by k plus 1, this is less than epsilon, and obviously 1 by k plus 1 by k is a point in S. So S, the 0 is the limit point of S. Okay. What are the other limit points? Well, so fix a m naught. Now consider the sequence 1 by n plus 1 by m naught. Now this sequence goes to 1 by m naught. So 1 by m naught is the limit point of S. So that's why S dash is equal to S. Union 0 is union 1, the set 1 by k belongs to natural number. So till now, just let me know, do you have any confusion, any problem? I will wait for 2 minutes, then we will go to the next portion. Okay. So let me know whether you have confusion or doubts. Well, I'll be back within 2 minutes. Well, so any confusion or a doubt? So it seems that there is a confusion and doubt. So going to the next problem. So the question is that is the set of rational closed in R? So yeah. So if Q is closed in R, then Q closure equal to Q, obviously. But since we know that Q is dense in R, that's a Q closure equal to R. So this together imply that R equal to Q, and this is the contradiction. So Q is not, sorry, it should be Q is not closed in R. Now we need to check that finite subset is closed. How to do that? Suppose x1, x2, x3, x4 finite subset. We need to check it is closed. Means what we need to show that all its green point will lie inside the set. Now observe that, consider the point x1. So consider the x2. I mean, if you can choose a small neighborhood x2, then this small neighborhood will, this deleted epsilon neighborhood of x2 will not contain any point of this set S. So all limit points, so set of limit points of this set is empty. That's why it contains S. So let me know, do you have any confusion till now? Well, so go to the next problem. We need to prove that A closure is the smallest, closure is the smallest closed set containing it. So for this we need to prove the following. We need to first prove that it's a closed set. We need to show that it contains capital A. We need to show the smallest such thing. So it's a closed set because its closure it's itself, that's a closed set, and obviously by definition of the closure it contains capital M. And now we need to check that it's the smallest closed set containing A. So suppose if it's a closed set containing. So since if contains, if contains A, so we can put the closure F closure, and so F contains F, so F equal to F closure because it's a closed set contains A, closure contains A, hence F contains A closure. So if it's a small, if so A closure is smallest closed set containing that set. So any confusion, any doubt, please let me know. So sorry. So consider A subset of B. We need to show that A closure is subset of B closure. So how to do that? Suppose X belongs to A closure, and suppose there is epsilon greater than G. So sorry. Since X belongs to A closure means what? For all epsilon greater than 0, B dash X comma epsilon intersection is non-empty. Now since A is subset of B, so B closure except epsilon and intersection B not. This is equal to B closure. That's why A subset of B implies A closure subset of B closure. Using this, we can prove that A union B whole closure equal to A closure union B closure. Logistically, can you tell me how we can prove this thing using the previous? Just can you just tell me if let's try at least. Well, so okay, so we are going through the proof. If you have any confusion, let me know. So first observe A subset of A union B. So A closure subset of A union B whole closure. So and similarly B closure subset of A union B whole closure. So A closure union B closure subset of A union B whole closure. Now we need to check the A union B whole closure subset of A closure union B closure. Now since A closure union B closure closed set containing A union B, so by the smallest property of the closure, A closure union B closure subset of A union B whole closure. Okay. So that's why you can prove that A union B whole closure equal to A closure union B. But well, this is not true for arbitrary case, for arbitrary union. Because consider this and this. Well, what is this? This is singleton is closed set, so its closure is itself. This is nothing but what is this? This is Q closure, which is R. So this union is union closure. I mean closure union commutes only for the excuse me, only for the finite case. For infinite case, this is not true. Now, and we finally show that closed and bounded intervals are closed sets. Is closed sets. Because any closed and bounded interval form closed AB and its closure itself, so it is closed. So yeah. So what we have started today, we have done a revision, a small revision here. So Location, just let me know, do you have any confusion or any doubt? Else we can continue some problem solving. Well, so check that A intersection B interior is not equal to A interior intersection B interior. So how to prove it? So we need to check that A interior intersection interior is not equal to interior. So observe one thing that A intersection B subset of A comma B. So basically A intersection B whole interior, sorry, subset of A interior comma B interior. So basically A whole interior subset of A interior intersection B interior. So, but the other but it should be but it is usually strict inequality because consider this example. A is equal to closed interval 1 2, B is equal to closed interval 2 3. So what is the open interval 1 2? B interior open interval 2 3. So A interior implies B interior is empty. But what is the intersection B? A intersection single interval. And so A intersection whole interior is 2. So this is non-empty. So only one side here holds. Okay. Also, one thing, there is one fact you can prove is that suppose AB is subset of R, prove that A cross B closure equal to A closure union B closure. How we can prove this? Once again. So, suppose first of all, A closure cross B closure is a closed set containing A cross B, and since closure is the smallest closed set, that's why A cross B whole closure subset A closure cross B closure. Now we need to check that A closure cross B closure subset of A union B whole closure. Well, let me repeat what we have just what I have told. We need to check that Cartesian product, the closure of Cartesian product of A and B is the Cartesian product closure of A and B. Observe that A closure cross B closure closed set containing A cross B. So A cross B whole closure such that A closure cross B closure. Now we need to check, and this is due to the fact that closure is smallest closed set containing that. We need to check that A closure cross B closure is also A cross B whole closure. So choose a point xy belongs to A closure cross B closure and choose epsilon greater than 0. By definition, we can choose a neighborhood minus this point intersection A cross B non-empty. This implies what? This implies Bx epsilon minus x intersection A cross By epsilon minus y intersection will be empty. Sorry, into non-empty. So this implies this part is non-empty and this part is non-empty. So this implies what? This implies Bx epsilon minus x intersection A non-empty and By epsilon minus y intersection B non-empty. So So X belongs to a closure and Y belongs to a closure. Okay. So this is one fact, and obviously it's note one thing is that so let xn be a sequence such that xn goes to x. Then this x belongs to the closure of the set S. If a sequence contains a point, then x is the closure of the set. How? Because choose epsilon greater than 0 since xn goes to x, this is what? Mod xn minus x less than epsilon. So this implies what? X minus epsilon, this mod xn minus x less than epsilon holds for all n greater than or equal to k. Just one second. So for all n greater than k, this is x minus epsilon, xn, x plus epsilon for all n greater than or equal to k. Okay. So this implies what? There is x minus epsilon, x plus epsilon minus x intersection. If you call this capital A, capital is non-empty. So this x belongs to closure of this set. So for example, consider the sequence 1 by this 1 by n goes to 0. So 0 belongs to this closure of 1 half 1/3 this. So we have already proved this in earlier in some other way, right? So this is another sequential approach. And it's one fact is that so x belongs to a closure if and or there exists a sequence xn in A such that xn goes to x. So it's a fact. We can get it in any book. The fact is that x belongs to a closure. Oh, sorry. This has been done in the class actually. X belongs to a closure if and only if there is a sequence in A such that xn goes to x. It is known as a sequential criteria. Of closure. Yes. Yeah. So that's it for today. Thank you. So yeah, if anybody has any confusion or doubt, please ask in the next live session that will be on Friday. Okay. So in the meeting.